We present an efficient paradigm for planning feasible trajectories for the center of mass and orientation of the body of legged robots. Such feasible trajectories maintain dynamic balance, while ensuring that the friction, actuation, and kinematic limits are not violated. The idea of the work is to develop a 2D feasible region, which guarantees such feasibility, whenever the projection of the center of mass lies inside it. The first step involves developing a feasible region guaranteeing dynamic balance and torque feasibility. Here, the feasible region is shown in gray, while the classical support region is represented by the dashed region. The black region is a scaled version of the feasible region used for planning. During the second step, we develop a reachable region, which guarantees the feasibility of the kinematic limits. Such region specifies the set of all possible center of mass locations that can be reached, with a specified orientation, without violating the joint kinematic limits. Note that a change in height of the center of mass, or the orientation of the trunk, can greatly affect the size, shape, and convexity of the reachable region. Finally, we can intersect the two regions that are defined on the same plane to get an improved feasible region. An efficient planning strategy is developed to ensure that the center of mass stays inside the feasible region. This simulation consists of HiQ robot descending a 30 degrees decline, while being attached to a rope, to explore a low-height tunnel. The aim here is to assess the influence of an external wrench acting on the robot, combined with a reduced trunk height, necessary to walk in confined places. Due to the mentioned conditions, the feasible region tends to be very small in size and is shifted forward. We compare the planning strategy based on the feasible region, with a heuristic approach developed in our previous work. Using the heuristics, the planned target for center of mass can be outside of the feasible region. As such, the whole body controller fails to achieve the desired ground reaction forces, and a tracking error of the COM trajectory follows. Using the feasible region, the planning strategy corrects the target center of mass determined by the heuristics, to be inside the feasible region. To increase the robustness of the planning, a scaled version of the feasible region, shown in black, is used. We validate the feasible region, and the center of mass planning strategy, in a scenario similar to the simulation shown before. Here the AlienGo robot is commanded to walk down a 45-degree ramp, while constraining its center of mass height to 20 cm. A rope is attached to the back of the robot and a counterweight is used. AlienGo, instead of HiQ, is used for safety reasons, and the kinematic limits are virtually lowered, to simulate those of HiQ. The planning strategy successfully maintains the projection of the center of mass inside of the region, and no violations in the joint kinematic limits were detected. On the other hand, the heuristic target results in multiple violations of the limits. We also test the strategy on HiQ, while walking at excessively reduced trunk height. The planning strategy, again, prevents the kinematic limits to be violated at a such constrained configuration. We can also use the feasible region to plan the target orientation of the robot. This simulation involves a complex non-coplanar terrain that particularly challenges the kinematic limits of the robot. A typical heuristic planning method, shown on the left, is to align the orientation of the trunk with an estimate of the inclination of the terrain plane. While this can be effective on a lot of terrains, it might not be sufficient on very complex terrains. You can see here that one or more of the joints reach its kinematic limits. With the feasible planning strategy, these violations can be avoided as shown on the right. Due to the unoptimized orientation of the trunk when using the heuristic approach, we can observe how the center of mass reaches the boundary of the feasible region, and eventually violates the kinematic constraints. The feasible region on the right is adapted to fit the center of mass trajectory, with the optimization of the orientation of the trunk. We also validate the feasible region for a trotting gait and dynamic motions. The feasible region becomes a segment, and moves according to the acceleration of the center of mass. the projection of the center of mass follows the feasible region, inferring that dynamic stability is achieved.